Thanks, Annie.
So welcome to Nerilie Abram for giving the seminar today. Nerilie did her undergraduate bachelor's at the University of Sydney. Then she did her PhD here at ANU, followed by a stint at the British Antarctic Survey. Then she came back in 2011 on a Queen Elizabeth II fellowship. She's currently a future fellow and was recently became a professor. So the beginning of the year. Congratulations, Nerilie. She's also well known for her success in the community and beyond, including receiving the Dorothy Hill Medal from the Australian Academy of Science in 2015. And this year she won the AMOS Australian Meteorological, is that right? Meteorological and Ocean Science, that's right? Oceanographic Society, excuse me, Priestley Medal. Today she's going to tell us about Australia's Black Summer and the connections to human-caused climate change. So welcome, Nerilie.
Thank you. Right, thank you to everyone who's here. Thank you to everyone who's online. This is quite a hastily put together presentation, and we're trialing this sort of format of delivery for the first time for our seminar series. So hopefully it works. Please bear with us if there are technical issues. For the people online, there will be an opportunity to ask questions at the end, and you can do that using the chat window. We've got Louis in here who's monitoring the Zoom, and so if there are questions that you want to ask via the chat window, then they can be relayed to me here, and we can go about that. Right, so I thought that I would talk today, and it's a little bit of a, I guess, a rambling reflection of the summer that we've just had, and that summer from the perspective of a climate scientist, and particularly sort of what it was like to be in that community where before the summer developed, we could see that this was primed to be a terrible summer for bushfires, what was done in terms of trying to communicate that, and where we kind of find ourselves at now in terms of climate science communication and the acceptance of the link between bushfires and climate change in Australia. Right, so, let's do this one first. Right, so I'm going to be, throughout this talk, actually sort of showing sort of some of the faces here who are communicating, primarily using sources from Twitter and the conversation. So you can see the experts who are communicating about the fire season that we've just had. So this was a tweet that came out just last month, reflecting on the outlook that was made back in August as to where in Australia it looked like we're going to be at above normal risk for fires. So that's the areas on this map that are shaded red. If you were to compare that map to the areas that actually burnt, even down to sort of looking at Kangaroo Island here in red, there's a very close correspondence between what was forecast in August of last year compared to what actually played out over the summer. So the fires that we saw in Australia were unprecedented in terms of the scale, the amount of land that was burnt, the amount of forest area that was burnt, and also the extent, the length of time that those fires burnt for, and the number of fires that were burning simultaneously. There are other aspects that weren't unprecedented. So it wasn't our worst bushfire season in terms of loss of human life, which is, I think, an excellent reflection on all the efforts that went into trying to protect people and property this season, all those adaptation measures that were able to be put in place. It also wasn't our most extensive fire season if you also take into account grass fires and savanna fires. So there we have an example from 1974-75 where we had a larger area of grassland that was burnt, but those types of fires are very different to what we're talking about when we're looking at forest fires. So if we look at forest fires, this was a correspondence piece that came out in Nature Climate Change a few weeks ago. What this is doing is across all these continental areas, looking at different types of vegetation and plotting over the last 20 years, what's the sort of the distribution of the amount of area burnt. The red line at the top there at 21% is how much of Australia's temperate and tropical forests burnt. And so you can see that that's well outside of the normal range of the amount of area that would be burnt during a summer, both in Australia and anywhere else in the world. This is an underestimate because this was an analysis done in January, so that was before we had the Namaji fires and the fires burning towards Breadbow. So what do we need for fire? There are 4 main ingredients that we need for fire. We have to have fuel to burn. That fuel needs to be dry enough to burn. We then, for getting large-scale fires, we need the weather conditions for that, for any fires that start, to be able to travel through the landscape, and we need a source of ignition. So what I'm going to talk about mostly today when looking at the links between climate change and the summer that we just had is particularly focusing in on the dryness of the fuel and those weather conditions as well. I'll talk a little bit about ignition at the end as well, but more in a reflection on some of the misrepresentation of science that happened while we were trying to communicate what was going on. So Australia's landscape was primed to burn ahead of this summer season. This is, again, from that correspondence paper, looking at the area of the forest area in Eastern Australia where the fuel was critically dry. And you can see 2019 standing out well outside of the range of variability that we've seen over the last 30 years in this case, as being in a state where if we had fire established in these landscapes, there was a lot of dry fuel there available to burn. So Mada Yebra, who's an academic at ANU, has done a lot of work looking at the dryness of our fuel. This is a tweet that she put out that weekend ahead of the fires in the Namaji National Park when they were threatening in Canberra. You can see, let's see here. So this is that fire. Here's the ACT in this area here. And the red colours here, the redder you go, the drier the fuels are. So this is where we were at as we were going into that weekend with bad fire weather and a fire already burning in the Namaji National Park. For contrast, this is what that same map looks like in a year like 2015. So you can see the contrast between those and just how dry the landscape was. So part of the reason why the landscape was so dry is that we've experienced a fairly intense drought in Eastern Australia over the last 3 years. So drought is a complicated thing. There's still a lot of research going on to understand exactly why we went into drought the end of 2016, early 2017. There are aspects of this drought that appear to be different from other droughts. So it appeared like that with this current drought, that the first signal to emerge was a temperature-related drying rather than a rainfall-driven drying of the system. And there has been a lot of confusion put out there in commentaries about climate change, about sort of to what extent are droughts directly or indirectly linked to climate change. So this is just showing the rainfall deciles over here on the left-hand side for the past 36 months up to the end of September last year. And then on the right-hand side for the last 18 months. And so you can see just how dry, particularly New South Wales, was. So we do have a variable climate. To what extent is climate change a factor in that? And so this is from the Bureau of Meteorology State of the Climate Report from 2008. looking at the cool season rainfall trends in Australia. And what you can see is that over the last 20 years, we've got a lot of red and orange areas on that map showing that our winter or cool season rainfall has been very much below average or the lowest on record compared to the full rainfall record for Australia, which begins in 1900. You do get a very different picture if you look at warm season rainfall. So warm season rainfall is traditionally the monsoon type rainfall. And so in that warm season, we see an increase in rainfall over northern Australia. So we have a contrast in those trends, both in where those trends are and the direction of them and the season that they're occurring in. But the main message from this one is that across southern parts of Australia, we're seeing a decline in the cool season rainfall, which is when this area gets most of its rainfall. This is the part of the country that most of Australia's population lives in. It's also where most of our agriculture is, which relies on rainfall coming in the winter. So to show a time series of that, this is looking at southwestern Western Australia. This is showing the precipitation relative to the median for the entire record. Brown colours obviously showing where it's drier, green colours showing where it's wetter. And so in southwestern Australia, there's a very, very clear drying trend. This part of Australia has lost about 20% of their winter rainfall since the 1970s. So you can see that very clear trend. In southeastern Australia, the trend is not quite as clear. But we do see that particularly since the end of the 1990s, we've had a succession of dry years and very few wet years. So what's going on with this? So the climate process that we need to look at to understand what's going on here is the southern annular mode. So the southern annular mode describes the position of the westerly winds, the storm tracks that sit to the south of Australia. And the position of those winds depends on the temperature contrast between the mid-latitudes in the southern hemisphere and Antarctica. So what we've been seeing and I will just point out, I'm going to come back to the southern annular mode a few times, and it's really important to note that the impact of the southern annular mode on Australia's rainfall depends very much on what season we're talking about. So at the moment, this is the annual average, SAM. This is the instrumental record that we have. It's a very short instrumental record, but it shows a tendency that we're moving towards a more positive SAM. So a more positive SAM means that we've got a greater temperature gradient between Antarctica and Australia, and those westerly winds then pull further south. They become stronger, pull further south. So that's the trend that we see in the observational record, and there's work that we did a number of years ago. Now looking at reconstructing the southern annular mode over the last 1,000 years to put that orange instrumental record into context. And so when we do that, we can now start to say that what we're seeing now is part of a longer term trend towards the southern annular mode becoming more positive. We can see that there has been a large range of natural variability of the southern annular mode over the last 1,000 years. But we are now in a mean state where the mean position of that SAM is in its most positive state for at least the last 1,000 years. Right, so when we have a positive SAM in the winter months, what that does is it pulls the storm tracks further south, and so that rainfall that we would normally be getting to southern parts of Australia in the winter, that cool season rainfall, the rainfall is still there, it's just that it's travelling around the Southern Ocean and it's not actually bringing rainfall to the Australian continent. So that's this situation here on the lower left of this figure. So we see that the westerly winds pulled further south. What that does is for southern parts of Australia, it means that there's less rainfall. So that's the brown colours on this map. So that's a trend that we're seeing. It's a trend that's very clearly linked to human-caused climate warming. And just to show sort of the projections of where that trend goes in the future, this is some model-based work for southwestern Western Australia, showing two different observational data sets where you can see that decline in rainfall for southwestern Western Australia since the 1970s. And then if you go and simulate that for the rest of this century with a high greenhouse gas emission scenario, this is what that projected rainfall trend looks like. And so you can see that the rainfall decline that we've already seen starts to look quite small and insignificant compared to what's projected for this area in the future. This is one of the parts of the world where we have the most robust agreement between climate models as to what we expect the future trend in rainfall to be. In southeastern Australia, if we continue on a high emission pathway, we also expect that we will see a decline in that cool season rainfall coming to southeastern Australia. But like what we see when we compare the instrumental records, there's a lot more variability in southeastern Australia. There's a lot more areas where that part of Australia can get rainfall from. And so there's less agreement between the models. And if we go into a low future greenhouse gas emission scenario, if we follow that pathway, then we may see that there's not too much long-term change in the rainfall in southeastern Australia. So it's very much dependent on which scenario we follow. Right, so there's a climate change impact there that's causing a dryness, causing the southern parts of Australia to become drier, particularly in the cool season. And so that contributes to the dryness of the fuel. The next thing I want to focus on was looking at the weather conditions that help to promote fire, and particularly the conditions where if there is a fire burning and you then get those conditions, you end up with a situation where that fire is very difficult to control. All right, so in Australia, the agencies that look at fire use the Forest Fire Danger Index. And what goes into that index is a combination of the maximum daily temperature, the relative humidity, the wind speed, and the drought factor. So that drought factor is capturing how dry the landscape is in terms of it being primed to burn. So like what I was talking about in the last section. And then we have these other things. So warmer temperatures add to the fire danger index. Low humidity and strong winds all increase that fire danger risk. So in terms of temperature, this is a global warming stripes image. So this is based on sort of a communication tool developed by Ed Hawkins at the University of Reading. So what this does is to visually represent the global temperature time series in a form of stripes. So for every year, there's a stripe, and the color of that stripe tells you about the temperature in that year. So this is a global average record. This is set so that the period between 1850 and 1900 has an average temperature anomaly of 0 degrees, and that's consistent with what's traditionally used or termed as the pre-industrial. So that becomes important when you think about things like the Paris Agreement, where we talk about trying to limit warming to below 2 degrees with an ambition to try and limit warming to 1.5 degrees above pre-industrial. So as you come along here, moving towards the right, you start to see the temperature, the colours becoming redder, an indication of that the climate is becoming warmer. Where we are now is with a global climate that's around about 1 degree warmer than that pre-industrial period. So 1 degree, our Paris targets are to try and limit that to below 2 degrees. In terms of Australia, this is what the Australian temperature record looks like. Again, annual average temperature anomaly for Australia. Australia's temperature data set begins in 1910, so we can't express this relative to that 1850 to 1900 pre-industrial period. So here the temperature anomaly is taken relative to 1961 to 1990. And what we see here is that 2019 was Australia's hottest year on record. The temperature was around about 1.5 degrees warmer than that 1961 to 1990 reference period. If we took an earlier reference period, so 1911 to 1940, then the summer, or the year that we just had in 2019 was 1.9 degrees warmer than that reference interval. So the world is warming. Australia's climate is warming, but 2019 was very extreme. As the climate warms, the forest fire danger index increases generally, and that's because there is a temperature component. So this is again from the Bureau of Meteorology State of the Climate report, looking at the trends in that forest fire danger index. And you can see all of these red and yellow areas are where we're seeing an increase in that fire risk because of increasing fire weather. There has been an attribution study that's been done on this just recently and submitted for review. That study, looking at the 2019 bushfire season, indicated that human-caused climate change, probably just from the temperature factor alone, caused a 30% increase in the risk of having that summer that we just had. Okay. So 2019 was extreme. December was particularly extreme. So December was when Australia broke its daily maximum temperature record. And so if we were to compare just December temperatures in Australia relative to where we are at with global average warming, we would say that that type of temperature in December is what we would expect with global warming of around about between 2.5 and 3 degrees. So here, Ed Hawkins tweeted this, saying that we experienced the future. Right, so that was a very extreme year. Another tool that we used in trying to communicate what we were seeing in Australia was to show the history of changes in precipitation in Australia compared to monthly maximum temperature. So this is an animation which I'll run in a moment, but just to run you through what's actually going to be shown here. So this is looking for Southern Australia. So Southern Australia is where we saw most of the bushfires happening over the summer. And what this is showing is, instead of annual averages, it's showing April to March averages. And so the reason for doing that is that it keeps the preconditioning, so the winter and the spring conditions that are important in terms of priming the landscape for whether it's going to be a bad summer for the fires. It keeps those attached to the subsequent fire season, and it prevents splitting our summer fire season over 2 different years. So that's what's shown here. The colours as we go through change by decade, and the diamonds indicate years where more than 1 million acres of forest burnt. So this is excluding grass fires and savanna fires, just looking at forest fires in Southern Australia. Right, so we run this animation. We can see there's actually quite an interesting linear relationship here that we see, where years that are cool also tend to be wet, years that are warm also tend to be dry. And then as we play this through, you can see most of those triangles plotting on the dry side, and the majority of them in the hot and the dry quadrant. And then you can see where 2019 and 2020 was to date. So sitting there as the hottest and driest extreme on that evolution that we've seen. So temperature and rainfall are important to Australia's bushfire risk. Okay, so Yes, so 2019, we have an ongoing warming trend, but we had very extreme conditions. And so it wasn't just a response to the slow warming, the slow and progressive drying trends. There was also an element of natural variability involved in what we saw that summer. So we're going to return to the southern annular mode. So overall, the southern annular mode is becoming more positive, and that means that in the winter time, we're seeing less rainfall in southern parts of Australia. Now, in 2019, in spring, we had quite an unusual event develop over Antarctica, and that sent the southern annular mode into an unusually negative phase. So opposite to the long-term trend. And what that did was in the spring and summer, it meant that those westerly winds were able to sit further north. And at that time of year, those westerly winds aren't bringing us rainfall anymore, but what they're doing is to draw hot and dry air from across the continent and towards the eastern part of Australia. So again, you see, if we have a negative phase in the summer, like what we saw in 2019, again, we end up with a lot of the brown colours in eastern Australia because we're drawing that hot, dry air across Australia rather than bringing rainfall. So in August last year, Unpa Lim, who's at the Bureau of Meteorology, published this paper in Nature Geoscience, looking at examples from the instrumental record where in the springtime, the polar vortex had weakened and in one case broke down completely. And then looking at what impact that has on Australia. And so what these maps are showing is that when we have that situation where in the stratosphere, the vortex over Antarctica starts to, or weakens rapidly, what we see is that the maximum temperature in eastern Australia is very warm, and also we end up with a rainfall deficit, so very dry conditions in eastern Australia. They went a step further to take that temperature and rainfall change and also look at what that meant in terms of forest fire danger index. I won't go through all of the details in here, but just drawing your attention to the plots on the right-hand side, so these red and orange ones. And what they're showing is the elevated risk in the forest fire danger index associated with these types of events over Antarctica. And what you can see is that for the October to January period, we get a very much increased risk of having high forest fire danger in the eastern parts of Australia, and particularly northern New South Wales and southeastern Queensland. This paper came out right at about the same time as two things. Firstly, there was evidence that we were seeing a very rapid warming over Antarctica and a breakdown of the polar vortex, like what had been studied for previous years in this paper. It was also the time where we started to see fires occurring in southeastern Queensland and northern New South Wales, and particularly burning in forest areas that wouldn't normally be susceptible to burning. So there's a nice conversation article about this put out by people from the Bureau of Meteorology, talking about exactly sort of what happens when we have this rare situation over Antarctica. So these events are very rare. In the Northern Hemisphere, these sudden stratospheric warmings happen roughly every other year. In Antarctica, we've only had one proper sudden stratospheric warming event in 2002. 2019 was not quite a full-blown reversal of the polar vortex, but was a very strong and rapid event. And so there isn't any indication yet from research as to whether there's a climate change signal involved in this. So this may have just been one of the things that's possible just because of natural variability. But this is one of the things that contributed to why we saw such an extreme year in 2019 and then leading into that bushfire season. Right, so we've got a sudden stratospheric warming. We've got global warming that is sitting at around about 1 degree above pre-industrial levels. We've got a long-term decline in Australia's rainfall that's causing the southern parts of Australia to lose cool season rainfall. That wasn't all that was going on though, because in 2019, we also saw a very strong positive Indian Ocean dipole event develop in the Indian Ocean. So the Indian Ocean dipole, again, it's one of our natural drivers of variability in Australia. And this is what our instrumental record of the Indian Ocean dipole looks like. Here, the two peaks here, this is 1994, this is 1997, which is the strongest event on record. And then this is 2019. This is the event that started playing out. So again, by the time it got to about August, it became clear that this event was establishing in the Indian Ocean, and that this would have implications in terms of how dry southeastern parts of Australia would be expected to be, and the implications of that for increasing bushfire risk. So what happens during one of these positive Indian Ocean dipole events is that we get cooler than usual sea surface temperatures off the coast of Java and Sumatra to the northwest of Australia. They're caused by increased upwelling that's drawing cooler subsurface water to the surface of the ocean. At the same time, in the Western Indian Ocean, the ocean temperature is warmer than usual. And the change in the surface ocean temperatures changes the atmospheric convection that's happening over the Indian Ocean, and in particular moves the convection that would normally be happening over Indonesia and providing an important source of rainfall to be drawn down into southeastern parts of Australia. That convection moves away and sits over Eastern Africa. So in Australia, we end up with dry conditions, particularly down in southeastern Australia. In Eastern Africa, they experience heavy rains and floods. That's what played out in this last summer in Eastern Africa. And over there's now a locust plague that's one of the ramifications of that heavy rainfall that happened in Eastern Africa. So there has been work done previously showing how positive Indian Ocean dipole events help to precondition bushfires, particularly in southeastern Australia and Victoria. So this is because when we have these events, we have very hot and dry conditions in there, it being drawn down into southeastern Australia. So the two plots on the left-hand side in the middle, are showing a relationship between the Indian Ocean dipole and soil moisture. So we see that the soil's drying out because it's hot and it's dry. And on the right-hand side, we see the relationship between the Indian Ocean dipole and the maximum temperature. So again, high maximum temperatures when we have this event set up in the Eastern Indian Ocean. So this is a plot that was part of this paper as well, showing plotting the years when Victoria had significant summer bushfire seasons, and comparing that to what state was the Indian Ocean dipole in, so positive or negative, so NIOD for negative, PIOD for positive Indian Ocean dipole events. And then the vertical axis there is also showing what El Nino was doing. So were we in an El Nino event or a La Nina event? And so the conclusion of this paper was that El Nino and the IOD are both important for preconditioning the landscape for bushfires in Victoria, but the relationship was strongest for positive Indian Ocean dipole events in this area compared to the influence of El Nino. Right, so when we saw this event set up, we had that indication from past research that we would expect there to be an elevated bushfire risk. This is just a snippet taken from the IPCC report that I was part of last year. So this is the Ocean and Cryosphere report. This is a statement from the Summary for Policymakers, talking about what we expect to happen in the future in terms of changes in El Nino and La Nina. You can see quite a bit of detail there and medium confidence in those statements. There's then a sentence that's sort of tacked on to the end about the Indian Ocean Dipole, saying that we expect these extreme events. So like what we saw in 2019, we expect those types of events to happen more often in the future, but only low confidence attached to that. The backstory behind this statement is that the original statement that was taken to the government approval session only had the statement about El Nino, but actually governments of the world pushed back and said, we actually want information in here about the Indian Ocean Dipole. Unfortunately, there hadn't been a really good and deep assessment of the Indian Ocean Dipole in that report, and so that was the best that was able to be done under those circumstances. What we have been doing, and this is research that came out last week in Nature, is to go and see what we can tell about the Indian Ocean Dipole by going further back in time. So we've been doing that using coral cores that we have collected from modern coral samples and also from fossil corals. This is a photo from a drilling trip that we did on Christmas Island a couple of years ago. So some people may or may not be able to recognise underneath all of that scuba gear. That's Jenny Malella and Oscar Branson, who are there doing the drilling on Christmas Island. Those samples aren't the ones that were used in this study, but it's a lovely photo to show what we do. This is the stuff that Jess Hargreaves is working on for her PhD. And then when we want to go further back in time, from the information that we can get from corals that are alive on the reef at the moment, we can then go and start looking at fossil coral samples. And in these fossil corals, so these are examples of fossil corals from Sunda Strait in Indonesia. I showed this one because you can see in this image on the left-hand side, the annual layers in that coral. These corals grow a lot like a tree. Every year that they're growing on a reef, they're recording, they're putting down a growth band in their skeleton. And what we do is to go and analyse the chemistry of that skeleton to reconstruct the climate conditions that those corals were growing in the past. So for this study, what we've been able to do is to build up 500 years of data about the Indian Ocean Dipole, so substantially longer than that instrumental record that I showed earlier on. We've been doing this study off the coast of Sumatra. And so the record that we've got is based on one modern coral and 8 fossil corals, some of which overlap in time. So this is the record that we have generated. There are still gaps in the record, and that just reflects where we haven't yet found fossil corals to be able to fill those gaps. And I don't expect you to be able to sort of see all of the detail in here. It's basically just a bunch of squiggles. But you can see those thresholds on there of positive IOD and extreme positive IOD, showing when in this data set we're seeing that those events have happened. Now the red triangles at the top are showing where we've got examples of extreme positive Indian Ocean Dipole events. And so across our 500 years of data, we only reconstruct 10 of these events. So these are very rare events. But what we have seen is that since 1960, we have 4 of those events. So in the last 60 years, we've got 4. Over the whole 500 years of data, we've only got 10. So that gives us a paleoclimate context to be able to see that when we look at the instrumental record and when we look at climate models and we see an increase in those events, the paleoclimate data is showing us that that is an unusual increase in those events. Now you may also see that the biggest peak on that graph isn't in the most recent part of the time series. So this is an event that we reconstructed in 1675. So it's the largest event that we have so far in our reconstruction. If we compare that to 1997, which was our largest event on record, then we would say that this event is somewhere between about 27 to 42% larger than that strongest event on record. So what that tells us is that what we've experienced in the observational period of time is not the worst that's possible in terms of how extreme the variability from the Indian Ocean can be. And so when we combine that with then the evidence that these events are becoming more frequent, that's something that is of concern. Now, obviously, with an event of this size, you would expect that there was quite an impact of that. We don't have the written history from Australia to be able to look and see what the impacts in Australia were. But throughout Southeast Asia, there is a lot of documentary evidence that we can draw on to see what happened during this year. And we do see that in that historical literature, there is information about an extreme drought in Sumatra. There were crop failures across Indonesia, but also in Thailand and India. And so there was famine. A lot of people died. And it's also been suggested that this climate event may have been one of the factors that contributed to war breaking out across Java around this time. Importantly, this was an event where there wasn't any historical evidence for a strong El Nino event, where in the past, a lot of these types of examples of this type of situation in Southeast Asia have been linked to El Nino events. In this case, we don't have evidence for an El Nino event, so we see the Indian Ocean playing a role. Right, and just to put that in context now, so these plots here, the purple curves are showing the number of positive events in 30-year windows, or the number of extreme positive events in 30-year windows. So purple is from our coral data and the instrumental data. So you can see that recent rise in how common those events are becoming. And then in red is the information that we get from historical and future climate simulations, where we run those simulations for the future under a high greenhouse gas emission scenario. So we can see that trend that we've seen particularly since the 1960s of these events becoming stronger and happening more often is a trend that we expect to continue if we continue on a high greenhouse gas emission scenario. And I'll just point out this nice piece that Nikki put together in the conversation. So there's more detail there on that, and also the link there to the Nature paper. Right, so 2019 was a very extreme year, and probably be described as a perfect storm for the bushfire season that developed. So we had record hot temperature. That was because of the long-term climate warming trend that we're seeing globally, but also exacerbated by natural variability. So it was a very extreme year for temperature. We've had prolonged drought, particularly in Eastern Australia over the last 3 years, which is part of a longer-term trend, and a trend that we expect to continue if we continue on a high greenhouse gas emission pathway. We had a very extreme positive Indian Ocean Dipole event. Again, we have evidence that this form of natural variability, this phenomenon, is being altered by human-caused climate change. So that these events are becoming stronger and they're happening more often. And then we also had this rare Antarctic southern stratospheric warming event where at this stage we don't have any evidence for or against as to whether we expect these events to be more frequent or less frequent in the future because of human-caused climate change. Right, so that was the setup that we had, and then we saw the impacts. On Christmas Eve, I was getting ready to turn my computer off and get into the Christmas holidays when I got a request from Scientific American to write a summary of what was going on in Australia and the links between the bushfires and climate change. I did say, like, it's Christmas Eve, I can't do it for a few days. And they said, that's okay, we don't think the fires are going to stop anytime soon. And so this is the piece that I put together a few days after Christmas. And then it came out on New Year's Eve in the US. And so actually it came out at that same time that we saw the terrible situation unfolding around Malakuta and the south coast of New South Wales. The link is there for people who want to go and have a look at that article, which summarises what I've just talked about today. And then following on from that, a group of scientists who have expertise in both the climate side of things and the fire side of things got together to put together an open letter about what the scientific evidence was between, for the link between climate change and bushfires in Australia. And this was largely motivated by the fact that in December we'd been, and before that, we'd been hearing politicians saying very clearly that they didn't think that there was a link between climate change and bushfires, and that now wasn't the time to talk about climate change. So this was a letter that we put together, and then we opened it up for other scientists with expertise to sign. So that was open for a week, and we had 446 scientists who co-signed that letter. Right, so touching back on this, I just wanted to just say a couple more things on the other things that were going on in terms of communication at this time and where we're at now. So one thing I haven't touched on is ignition. I guess I didn't also talk about fuel to burn. So fuel to burn, that's something where we can help to adapt to increasing bushfire risk through measures like hazard reduction burning. That was something that came up in the discussion of this a lot. So people who didn't want to talk about the climate change aspect were putting this down to, there was a problem that people hadn't been doing the hazard reduction burning. The other thing that came up was ignition, and particularly talk of arson in this. And so the link to arson is actually an interesting conversation article that was done looking at the conversation that was happening on Twitter, and identifying that it looked like there was actually a bot campaign in terms of trying to change the dialogue so that instead of talking about a climate emergency, this situation got turned into an arson emergency. And so a very large number of the tweets, the Twitter accounts that were looked at in here had suspicious activity that was what you would expect from a bot that's putting out information rather than being a genuine person having a discourse on Twitter. Interestingly, one of the examples that they pulled out in that article was based on the article that I'd written for Scientific American. You can see the hashtag that they were trying to push for arson emergency. Some other things that have changed since then. So since January, at least the official line from politics is that we can now link climate change and bushfires, and we can put them in the same sentence. There are still some voices out there that are trying to downplay that link or to distract with other aspects. We also have people like columnists like Andrew Bolt, who in this column talks about they've never denied that the planet is warming, but instead warming is good for us, of course. So that's where we find ourselves now in the political discussion. There is more of an acceptance that climate change is real, that there was a link to the bushfire season. It remains to be seen whether we actually get action on that, or whether any action that's taken goes more down the adaptation line rather than the actual mitigating against the underlying climate warming problem. And then I just thought I'd show this. This is a diagram that I put together a couple of weeks ago. I was on a climate change panel for a meeting in Sydney for people who are on the board of directors for companies in Australia. So that was a very interesting forum, and particularly in every single session that I went to, climate change was mentioned. So these people, people who are on the boards of companies, are very aware of the climate change problem. They're openly talking about it and the risks that it poses to them. And so that was actually quite a positive moment to actually see that there is the potential for action coming from that sector. And so in this panel, I was allowed to present one slide. This was the slide that I showed. So again, this is the climate strikes from 1850 through to 2019 with observational data. And then that's continued through to 2100 based on contrasting what happens if we're on a high emission pathway. And so under that pathway, we end up by 2100 with warming of over 4 degrees above that pre-industrial level, compared to if we're on a low emission pathway that's consistent with the target of the Paris Agreement, where we do have a 2 in 3 chance of levelling off temperature to below 2 degrees above warming. So that's kind of put up there just in terms of the situation isn't all doom. We do expect the risk for bushfires to increase as climate warming continues because, and we see these, our fire risk being affected in multiple ways. But what we can say is that that risk, how much that risk increases will be much less if we end up on a low emission pathway compared to a high emission pathway. Right, and I can't end on that slide, so I thought I'd end on a happier slide from a recent trip to Rottnest. So thank you, everybody. So people in the room, I'm happy to take questions, and Louis, if there's questions on the online chat windows, I'm happy to take those too. Yes. Any questions in the room? Yeah. Yeah. So what we're seeing as the climate is warming. Oh, sorry. Thank you. So the question was, how is climate warming influencing the Indian Ocean Dipole and the SAM? Is that correct? Yep. Yeah, so what we're seeing as the climate warms, the ocean is warming, but it's not warming at the same rate everywhere. So at the moment, the Western Indian Ocean, because of human-caused warming, is warming faster than the Eastern Indian Ocean. So what that's doing is putting the Indian Ocean into an average state that is more conducive to having these positive Indian Ocean dipole events. And so by changing the mean state, we're making it easier to have those positive events set up because the West is warming faster than the East. For the southern annular mode, there's an influence there both from greenhouse gas warming, but also the influence of changes in stratospheric ozone. So the ozone effect is particularly strong in summer, whereas the greenhouse gas influence is a year-round event. And in the future, we expect the greenhouse gas influence to be the dominant one as the ozone hole recovers. But what we're seeing is that at the moment, parts of Antarctica are warming and warming quickly, but on average, the temperature over Antarctica is warming not as fast compared to the temperature of the mid-latitudes. And so that's setting up an increased temperature gradient between the mid-latitudes and Antarctica, and that's what then causes the southern annular mode to move into a more positive phase with the western winds becoming stronger and shifting south.
Yeah, I'm just going to have one question on so first of all, we have a couple of one out of the audience in case people are thinking on the so the question, so this is from Katie, saying regarding the relationship between iodine and linear, are there premium climate teleconnections and or iodine expressed differently depending on the states, or is converted more central Pacific warming?
Yep. Yeah. So Katie was asking about the impacts of the IOD and ENSO, I think, acting together, but also the impacts of different flavors of El Nino. So Eastern Pacific versus Central Pacific El Ninos. Yeah. So the different phases of El Nino do have different rainfall impacts because the temperature anomalies sit in a different place. I haven't seen work. I would guess that work has been done. I actually haven't read work about what that does in terms of the fire risk for Australia for one versus the other. What we're seeing at the moment is that Central Pacific El Nino events appear to be becoming more frequent, but the Eastern Pacific El Nino events that we have are becoming stronger. So that's sort of that aspect, but I haven't really answered it in terms of fire because I don't actually know off the top of my head the overall specific answer to that. The more generalised answer is that an El Nino event increases bushfire risk in Eastern Australia, and in some parts of Australia, that's actually sort of the dominant effect in terms of all of the different types of modes of variability. I didn't talk about it today though because El Nino was in a neutral state over 2019, and so it wasn't one of the players in terms of what went on in the last summer. In terms of the links between the Indian Ocean Dipole and the El Nino, what we've been able to show, particularly in that study that came out in Nature last week, was that there is quite a close connection between the variability of the two ocean basins. That doesn't mean that you can only get a positive Indian Ocean Dipole event when you have an El Nino event. That is a combination that is quite likely to occur. So when you have an El Nino event, you help to promote the ocean and the atmosphere conditions that are conducive for a positive Indian Ocean Dipole at the same time. But like what we saw in 2019, like that 1675 event, also like 1961, we do see years where we have a positive Indian Ocean Dipole event without there being an El Nino, a positive IOD event, sorry, without there being an El Nino event at the same time. But what we can see from that 500 years of data is that over the last millennium, periods of time where we've seen reduced year-to-year variability of the Indian Ocean Dipole correspond with periods of time where there's been a smaller swing between El Nino and La Nina events in the Pacific. And that looks like it's actually quite a close relationship that holds at least over the last 1,000 years.
Well, I'm going to draw this to a close because I've noticed the time.
There are some more questions, but perhaps we
Yep.
really brief. I think because we don't normally have questions in written, we can't normally answer them offline, but we can actually ask really interesting questions to follow.
Yeah, so let's take
those.
those offline, and we'll talk to Nerilie about potentially posting the answers to those questions as well. We'll ask you to do the same. Okay, so
thank you.
Thank you very much. Please join with me in thanking Nerilie.